All right, so just this last lecture, right, we learned about adding HBr across a double bond, and we said that this would then give us the Markovnikov product, in which case our Br will go on the more substituted side, right? So we'll call that Markovnikov. And so that's cool. That's how we get that product. But we as synthetic chemists want complete control. So is there any way that we could add something across this double bond and get the anti-Markovnikov product? Right. The anti-Markovnikov means that this bromine is going to go on the less substituted carbon. And so can we do that? And the answer is yes. But in order to do this, we have to avoid carbocations, right? Because carbocations are what cause the Markovnikov addition. And so the way we do that is through the use of radicals. So they're not quite going away. And so what we do here is we have our alkene. We add some HBr across it. And due to the thermodynamics here, it's only Br that works. Chlorine, fluorine, and iodine won't work. And then what we do to it is add some ROOR and heat it. This ROOR, these R's can be hydrogens or carbons attached to something else. And this is just a peroxide. So anytime you have this single oxygen-oxygen bond, you have a peroxide. And this bond is very weak. And with the addition of heat, will undergo homolytic cleavage, right? And so this is what's known as a radical initiator, because it's going to start making some radicals, right? So you heat this up, it's going to homolytically cleave into two radicals. And so this is going to be the basis of our mechanism here. So the first step here is you're going to form the radical. Right, so we have our ROOR, heat this thing up, you get some homolytic cleavage. The second step is going to be some propagation with HBr, right? Due to thermodynamic reasons, this radical is first going to react with HBr. So we have this radical, we've got HBr, and it's going to form an OH bond, right? An alcohol bond. So ROH plus our Br minus. And then in this third step, which is the star of the show, we have hydrogen abstraction to form the more stable radical. So we have our alkene here, we have our radical bromine, and it's going to interact with this double bond to form a bond with it, right? And so now the question is, we can go one of two ways, right? This other electron can go this purple route or this green route, right? It can go on one of these carbons. So let's think about these two products. On the one side, we'll have going purple. On the other side, we'll have going green. And so if we go the purple end, right, our radical end up there. And then if we go the green end, our radical will end up there. And so if we think about what's more stable, right, this is a secondary radical, this is a tertiary radical. Secondary or tertiary beats out secondary, and so our predominant product will be the one on the right. And so you can notice that now our bromine is on our less substituted carbon. And then step 4 here is further propagation to form more bromine radical, right? So we have our tertiary radical right here. It's going to interact with another molecule of HBr to complete our reaction, and then produce some more bromine minus, which can go back into, what was that, the second step, I think? Third step and go back into the third step and continue the reaction, so on and so forth. And if you think about the end result here, we have an anti-Markovnikov addition. And so you can see how using different reagents, we can get the product that we desire, right? So if we start off with an alkene that is not symmetric, right? We can insert a bromine on whichever side of the alkene we want, right? We can put that bromine on the less substituted side, or we can put that bromine on the more substituted side, right? On the left, this is the Markovnikov addition. On the left or on the right is the anti-Markovnikov addition. For the product on the left, we want to add some HBr. For the one on the right, we add some HBr, but we add some radical initiator and some heat to form this alkene to get our product, right? And think about the intermediates here. On the left side here, we'll have this carbocation where a nucleophile can then attack. Whereas on this right side, we add that Br bond first, and then the hydrogen gets added second, so the more stable radical forms. So it's all about what intermediate you form. And of course, no matter which pathway you go through, carbocation or radical, they both lose their stereochemistry. And so your end product will be racemic no matter which pathway you take.